this is Team24 reading out on our chest X-ray diagnosis using deep neural networks. Our objective is to train a convolutional neural network to detect and accurately diagnose chest pathologies. To that end, we'll cover our problem description, related work, experimental setup, approach, results, evaluation, and future work. Thoracic diseases are widespread, serious diseases killing tens of thousands of people annually. Chest radiographs are the cheapest and most commonly used screening tool to diagnose thoracic disease early when the disease is easier and cheaper to treat. However, accurate diagnosis requires expert radiologist knowledge and experience, and with the increasing volume of radiographs to read, mistakes can be made, and scaling to the health need is a problem. With the advent of deep learning and its effectiveness with image classification problems, convolutional neural networks, CNNs, can be used to scale the expertise of a radiologist. We reviewed published papers for prior work in the space of using CNNs to perform diagnostic classification of images. Some themes we found as part of this review include improving the performance of classification by using pre-trained models like ResNet-50, and including non-image demographic data in the training model to improve accuracy. We also discovered a recent implementation of a ResNet-50 image classification algorithm in AWS SageMaker, which had comparable results to recent top industry performance on the improved NIH Chest X-ray 14 dataset. Generally, the flow for our data pipeline was to perform ETL and pre-processing of image and demographic data within Apache Spark on Hadoop. This produced summary statistics and a balanced dataset split of train, validation, and test. We also created a second dataset using normalized demographic data, painting a stripe of 6 data points in the rightmost 6 pixels of all rows in each image. We called the original dataset Raw Image Dataset and the new one Demo Image Dataset. Statistical exploration and analysis were performed on the demographic data that accompanied the NIH images. Disease, age, and gender frequency were graphed. Data was carefully split into train, validation, and test sets to preserve a consistent disease frequency in each dataset. We used 2 separate software stacks to work on the data pipeline. One was the Apache Spark 230 with Scala 2, 1112 on Hadoop 275. We also used Python 3.6, NumPy, and CV2, both on the desktop and on AWS SageMaker with Jupyter Notebook 560. For hardware, AWS uses 3 machines in SageMaker: a notebook instance which coordinates the training and prediction activities, a training instance which uses heavyweight V100 GPUs for learning the train data, and an endpoint instance on which to deploy the trained model and perform test classification prediction. In our study, we used the instances that are shown below. After ETL, data preprocessing, and feature engineering, the summary statistical information was produced, as well as a CSV file dictating a balanced dataset split for train, validation, and test. All training was performed via SageMaker Jupyter Notebook using the image classification algorithm. Experimentally, we tried a long training instance with 100 epochs to find the optimal number of epochs. And then we trained variants of the CNN model at 128 and 256 batch size, using the raw images for training. For comparison, we trained a 256 batch size CNN model on the demographic dataset. We were able to capture and plot the training and validation accuracy for each of the models during the training. And the top performing model was the demographic dataset with 80% validation accuracy by the 25th epoch. For AUK and F1 scores, the raw data performed better, and the 256 batch size was best for AUC and 128 was best for F1. We evaluated our results in comparison with earlier work as shown here. Because some of that earlier work only evaluated on the chest X-ray 8 dataset, we truncated our findings to just the relevant 8 diseases here. In addition, comparison was made using AUK, due to the findings being reported in AUK in prior work. We found that our results were on par with or better than the results in prior work in 5 of 8 of the cases. One result, pneumonia, was not available due to lack of sample size in the test data set. We have many ideas toward future directions of work in this space, but I'll highlight one here. Although the demographic dataset did not perform as well as raw images, it was not far off, and we do believe it has promise. We would definitely look to improve with hyperparameter tuning and additional training to make it a more effective classifier. These are specific references we had in our presentation. The full list of references and resources is in our paper. We enjoyed participating on this project, and thank you for the opportunity to work on this and present our findings.